Swayam Prabha. Digital India. Educated India.
This is lecture number 43. Hello everyone, welcome back. We have got almost all the gradients that is required in CFD to basically solve a fluid flow problem. We have looked at the governing equations, we have looked at the different discretization approaches, flux schemes, the properties of the flux schemes, discretization schemes. Then we also looked at the finite difference approach, finite volume approach. We solved some small problems and also we solved the shock tube problem, right. So, now the only thing that is ideally required is the boundary condition, and we will have the discussion about the boundary conditions very soon. But there is one piece which is very puzzling and that needs to be solved is the aspect of the turbulent flows. As you might be knowing that most of the flows that are around us are basically turbulent flows, right. You look at smokes that is coming out of a chimney, the flow is turbulent, right. You can look at the flow behind an aircraft or flow behind a car, the flow is turbulent, right. So, it is not that the equations that we have learnt, that is the Navier-Stokes equations, cannot solve that problem, right. It can solve the problem. We have the scheme, we know the schemes, we know the equations, we can discretize it, put a grid and try to solve the problem. But when you try to solve that problem, any turbulent flow problem at a sufficiently high Reynolds number, I will come to that number Reynolds number again. We have discussed or we have seen that Reynolds number while non-dimensionalizing the Navier-Stokes equations, but that is the number. I am just jumping ahead here. That dictates whether the flow is going to be laminar or turbulent, right. So, if the Reynolds number is sufficiently high, let us say if you are talking about a wing or an aircraft, right. So, the Reynolds number typically is around a million, right, or several millions, right. At that high Reynolds number, if you try to use the Navier-Stokes equation, put a grid and try to solve it, you will run into trouble, and the reason for that is if the Reynolds number is very high, you will have several scales in your flow. Okay. So, if you have like let us say 1 million Reynolds number, you have separation of the scale, that is in other way the separation of the grid size is of a million or the order of a million. So, if a smallest scale is let us say 1 millimeter, then the largest scale will be 10^6 millimeter, right. So, that is the kind of scale that you are talking about, right. So, you will quickly see that your grid size will become very large. So, I talked in one dimension 1 millimeter to 10^6 millimeter, it can go to in the 3 dimension, it will go to 10^6 power 3, right. So, your grid size will become humongous and it can become so big that for a practical flow problem you just run out of the computing capability. Even if you use the largest exaflop machine, petaflop machine, exaflop machine that is available now. So, flop is basically floating point operations per second, right. So, that is a measure of how much computing power one computer has, right. So, typically it is talked in terms of the supercomputers, right. So, even if you use the fastest supercomputer or the most capable supercomputer in the world, you cannot solve the problem directly if the flow is turbulent, right. Then how do you solve that? In fact, in most cases you might be using some kind of commercial software or an open source software. You must be getting the answers, and there are many aircraft that have been designed using these softwares, right. The cars, aircraft, wind turbine, turbine blade, anything you name it, and we have been using CFD to basically predict the flows on these geometries at realistic Reynolds number and realistic design conditions. So, how are we doing it? Where is the catch? So, that is the puzzle that we are going to look at today. So, basically we want to know how the turbulent flow works, right. If you understand the characteristic of turbulent flow, we may probably answer this puzzle or basically try to find out a way so that we do not need to use that kind of computing power as we have in the direct numerical simulation. And that means using the Navier-Stokes equations as it is to solve a complex turbulent flow problem at sufficiently high Reynolds number. Okay. So, so the topic today is the simulation of turbulent flows, right. So, before we go to the turbulent flows, I want to emphasize the difference between the laminar flow and the turbulent flow, right. So, this goes back to the very old experiment by Osborne Reynolds, I think done around 1893. The Reynolds number is after this person. So, his name is Osborne Reynolds. Okay. So, the Reynolds number is behind this person. So, what he did, he designed a very intelligent experiment, and you can see the setup of the experiment on the right hand side here, right. So, what he did, he took a water tank and connected a glass tube to that, right. So, glass tube is so that you can see what is happening inside that flow, and then he put a valve here, you can see the valve here. So, this is the valve that he has put, okay, in the tube. So, if you open the valve more, then the flow rate will become higher, right. And then he introduced the die in between the tube, so that it does not disturb the flow. Okay. So, it is basically sufficiently away from the valve, and then what he did, he started opening the valve slowly. Okay. So, initially when he opened the valve, so what he saw, like if let us say this is my tube. Okay. So, what he saw is basically if the flow, the die is like this is a red color die, if it goes in a line, it is actually going in a line, it is not deviating. Okay. So, you can have different lines, okay, and they are along a line, okay, they are not changing. Okay. So, in other words, the flow is smooth, right. So, the flow is smooth, no disturbances. Okay. Even if there is slight disturbances, they get dammed out, okay, and he called these kind of flows as the laminar flows. Okay. Remember, this happened when he did not open the valve fully, right. So, the flow speed was quite low. Then what he did, he basically increased the speed, right. So, now let us say this is second time when we increase the speed. Okay. Let me make the valve same size of the tube, okay, maybe around here. Okay. And he found that now it is slightly wavy. So, it comes like this and then it become slightly wavy. This is when the speed is increased slightly. Okay. And then what he did is he further increased the speed, and then what he found is basically now it is like there is so much zigzag, so much disturbances all over. Okay. They are not basically staying in line. Okay. So, this you can see that now they are no longer very organized as we had earlier. So, this was an organized flow on the top, and this is the flow at the bottom is basically not organized, okay, very violent, there is mixing all over everywhere, right. So, he termed this flow as the turbulent flow, okay, because it is turbulent, right. This is laminar, this is turbulent, and in between you can have flow which you can call as the transitional flow. Okay. Now, what he did that now he basically changed the liquid. So, earlier he did with water, okay, then he made it a little bit more viscous and tried seeing that what is happening. He of course observed the same phenomena, it was initially laminar and it became turbulent, but it happened at different speed, okay, different flow speed. So, then he experimented with different liquids with different density, different viscosity, and he tried finding out that what is that parameter which governs whether the flow is going to be organized or flow is going to be disorganized, right. So, then he came up with a Reynolds number, okay, with a number which is now known as Reynolds number, which is a non-dimensional parameter which is given by rho u L by mu. Okay. In this case, because it was a tube, so L is the length scale, so that becomes d. So, this is basically in this particular case this is rho u d by mu. So, it does not depend on just the velocity, okay. It also depends on your density, your viscosity, and the shape and the size of your instrument that you are using, right. So, in this case it is tube, right. So, this number I am sure you are already aware of, you have done the fluid mechanics course. Okay. So, you can see this as basically ratio of inertial forces, okay, by viscous forces, because viscosity is at the denominator. Okay. So, as you can see, if the Reynolds number is low, okay. So, let us say Reynolds number is low, typically let us say Reynolds number is less than 2000, okay, for a pipe flow. Okay. As I told, it depends on what kind of instrument that you are using, or what kind of vessel that you have where the flow is happening. So, here it is tube, let us say it was a channel or something else, then that number will be different. If it can be a flat plate, right. So, let us say if Reynolds number is less than 2000 in the case of pipe flow, then he observed that the flow remains laminar. Okay. And then when the Reynolds number was greater than 4000, okay, for the same flow, he observed the flow was becoming turbulent, right. So, remember this 2000 and 4000, it is not a sacrosanct number, number can change if you can make the environment very quiet, right. So, let us say that you can make the pipe completely smooth, there is no friction there, okay, and the environment is also very quiet, then it can basically increase this number to a very high value. Okay. There are super pipe experiments in Princeton where they have observed that they can maintain the flow to be laminar to a very high Reynolds number. Okay. But typically for our understanding, we take that, okay, in general situation, if the Reynolds number is less than 2000, the flow is laminar, and if Reynolds number is more than 4000, the flow becomes turbulent. In a pipe flow, in the bond-layer flow, it will be a different number, in a channel flow, it will be a different number, right. But what we understand that we need a basically combination of all three, okay, all four to basically get the value of the Reynolds number, and that will dictate whether the flow is laminar or turbulent, right. So, you can also write it in terms of, you can take this rho at the bottom, and this becomes u d by nu, okay, where nu is now the kinematic viscosity, right. So, this is what I was saying, that this is the typical picture of the laminar flow. The if the flow is happening in the laminar region, if it goes like this, it will continue to move in that line, but in the turbulent flow there will be a lot of mixing, right. There will be, I use the term called eddy, okay. You can see these shapes here, okay. So, these are basically kind of your eddy shapes. So, what they do, basically they do a lot of mixing, and depending on Reynolds number there will be violent mixing from top to bottom, okay, and that actually develops additional stress also. Typically you would hear that the turbulent flow has higher drag, right. If there is a wing and the flow is turbulent, the drag is higher, okay. Why? Because it develops higher stress, that is because of this the momentum that is being transferred by these eddies, okay. And this is a picture in the same pipe, right. So, if this is my pipe, okay, and if the flow is laminar, your velocity profile will look something like this. It will be a parabolic profile. You all have solved this problem, okay, in a quiet flow, Poiseuille flow, right. It looks parabolic. So, you have the maximum velocity here, and there will be no slip condition here. Basically, the velocity goes to 0 at the boundary, okay. So, this is my wall on top and bottom, okay, and the velocity goes to 0 at the wall, right. On the other hand, if the flow is turbulent, you would see that it becomes something like this, okay. It is now more flatter, more fuller, okay. If you compare the region, if let us say if I zoom in this region, say if I take this region and zoom that in, okay. So, how will it look? So, this is my wall, okay, and your laminar boundary layer is going something like this, okay, and your turbulent boundary layer will go something like this, this is your turbulent and this is a laminar. Okay. So, what is this? This is my velocity profile. I am plotting the velocity here. Again, you may ask that I just told that there is a lot of mixing, then how can the profile may look so smooth like what I have drawn here, right. So, again there is a point here that what I am drawing here is not the instantaneous flow profile. That means that it is not a measurement at a given time, but let us say I measured it over some time and then I take an average of that. Okay. Or what I can do, I can repeat the same experiment many times and take an average of that. That will make the profile smooth, and that is what is called the mean flow profile. Okay. So, that is denoted by a bar sign. So, here in the laminar case anyway there are no fluctuations, okay, no eddies. So, then it is a smooth profile. On the other hand, if you look at the turbulent profile, here for example, you can see there is a lot of waviness if you measure at any instant, and this change every time. Okay. This, let us say you took at one time it looks like this, okay, another time it may look like this, okay, and then another time it may look like this. Okay. But when you take the average of that, then it becomes a smooth profile, but it is different from the laminar profile. That is the point I am trying to make, right. The slope here, in this case the slope near the wall in the turbulent flow is much higher. So, if you so right now this is u and this is my you can call it y. So, this is x axis and this is y axis. In this case also this is x axis, this is y axis. So, this is if you call it du by dy. Okay. So, this is in turbulent flow is higher than the du by dy in the laminar flow, right. So, this is the laminar flow. You can see the so what is happening. So, let us say this is my profile in the free stream. Okay, this is the velocity that is getting in the free stream. So, it goes to that free stream velocity in a much quicker time, right. Let us say it reaching the free stream velocity somewhere here, okay, or maybe let me draw here. Okay, it reaches the free stream velocity in this particular figure around here, right. So, this becomes like this. Let me erase the other part. Okay. So, it reaches somewhere here, and here you can see that in order to get to that velocity, it basically takes a very long length in this direction, right. So, if this is my u and this is my y, so this du by dy is smaller here, right. Why? Because it has to go to 0 velocity, the velocity is 0 here, right. It went to u, but it took a very long distance to get to that u. Here in this case it took a very small distance to get to the u, and why it is happening? Because of the presence of the eddies, it quickly generates momentum, and going from the no slip to the free stream condition, it takes much smaller distance. Okay, but it has to maintain the no slip condition. So, it has to go to 0 at this point. So, to go to this free stream, it will take a smaller distance, okay, and that is why this du by dy will be higher in the turbulent flow. In the laminar flow, it will take a longer distance, okay, this is the distance it is taking. So, that is why your du by dy is smaller in the case of laminar flow, and that can be related to your wall shear stress, right. I made a statement that the wall shear stress in the turbulent flow is higher. You can see that how. So, the wall shear stress is defined tau w is equal to mu du by dy, mu you can write it mu wall at y equal to 0, right. So, let us say this is your y equal to 0, you can take either side, this or that side, or if you are doing a flat plate, okay. So, this is your profile. So, this is your y equal to 0, okay. So, because your du by dy is 0 is higher at y equal to 0 in the case of turbulent flow. So, that is why the wall shear stress in the turbulent flow is higher than wall shear stress in the laminar flow, okay. And remember, this viscosity is the property of the fluid, it does not change, because of the change in gradient you are experiencing a higher stress, and that gives you the drag. So, that is why this wall shear stress related to the skin friction drag. Okay. As you might be knowing, there are mainly two kind of drag, one is a form drag, other is the skin friction drag. So, the form drag is because of the shape, and the skin friction drag is because how the flow is sticking to the wall, right. So, that is why the drag in the case of turbulent flow is higher than the drag in the laminar flow. Of course, there are other considerations that you should keep in mind, that if the flow is turbulent, then there is a chance that the separation may be delayed, right. Let us see, if you are trying to simulate flow over a cylinder or study flow over a cylinder. If the flow is laminar, okay, it may separate early, okay, it may separate here, okay, if the flow is laminar. On the other hand, if the flow is turbulent, it may be delayed and it may separate here. Okay. So, the separation introduces another drag, okay, because it changes the effective shape, the form drag changes. So, there are other considerations also, right. So, that is why you might be knowing about the flow control techniques on the wing. So, let us say if the wing, the flow is separating, you put some kind of vortex generator. What it does, it makes the flow turbulent, and that is why the separation is avoided. Okay, but that is not something that we are going today. We want to first emphasize that how the different boundary layers look like, the laminar boundary layer and the turbulent boundary layer. Okay, but we have still not gone to the problem that why the turbulent flow is difficult to simulate. Okay. So, let us look at some of the flow pictures of the turbulent flow. So, this is for example flow in a jet. Okay, what you see, you can see that there are so many kinds of scale here. Okay, you can have one scale you can think of as okay, this is a very big scale here, and then there are very small shapes that you can see here. They are very small eddies, right. But if you take a mean of that, if you basically time average it for a long time, then you will see that all these small shapes disappeared, and what you look at is a very nice mean flow. Okay. Similarly, if you look at the boundary layer, you have like so many scales and so many phenomena that is happening here. Okay, you can see at the bottom picture, and if you average that out, it looks quite smooth. Okay, and this is how your the velocity boundary layer will look like. Okay, now let us delve little bit more into the turbulent boundary layer. Okay, so the turbulent flow can happen in two situations. One is the called the free shear flow. Okay, so in the free shear flow, there is no wall shear. Okay, it can come out of a wall, for example, in a jet, but after it comes out, it is developing on its own. Okay, so there is one called free shear flow. You can have jet, you can have wake. Okay, and the other is basically wall bounded flows. Okay. Now, wall bounded flows are another situations which makes the thing difficult, right. Why? Because whenever you have wall, right, you have to apply the no slip boundary condition there, and once you apply the no slip boundary condition, let us say you have developed some algorithm which nicely works, it gives you the nice structure in the form of matrix, but then you have to put the values u and v and w equal to 0 on those walls, right. So, then all your CFD algorithms need to be basically somehow account for those boundary conditions. Okay, but most of the situations that we are dealing with are the walls, right. You want to design a car, you want to design an aircraft, you want to design a turbine blade. Okay, you want to design anything, it has got a wall, right. The flow will stick to the wall. So, no slip condition has to be satisfied, right. So, to discuss the wall bounded flows, we need to know that how the boundary layer gets developed on the wall, right. So, that is why we will discuss little about the turbulent boundary layer, that how the flow looks like on a flat plate. So, flat plate is just an example, okay, but you can generalize it to anything, right. You can generalize it to let us say a wing or a turbine blade or an airfoil, a cylinder, whatever thing you want. Okay. So, this is a typical picture of the boundary layer. Okay. So, you can see that initially you have a laminar boundary layer, the flow looks nice and smooth. Okay. And then in the between you have a transition region. Okay. So, flow starts getting unsteady. Okay. You may have some spots of the turbulence getting developed here, okay, and finally, it becomes fully turbulent in this region, right. So, this is how typically flow develops. The flow is coming from left to right, and this is the edge of the plate. Now, if you look at any layer, so this is my typical profile. Okay, this is the profile that you have. Okay, you can divide that profile into two parts. Okay, one is the inner layer, another is the outer layer. Okay. So, inner layer is the region where the viscous effects are important, okay, or the viscosity is important. Okay. So, so I'll discuss about those inner layer, but you can further divide this inner layer into two parts, and that typically accounts for like 50% of your 15% of your bondilayer thickness is the inner layer. You can divide into two parts. One is very close to the wall, okay, and that is called the laminar sublayer or viscous sublayer. Okay. So, I will use the word viscous sublayer, okay, because the viscosity plays the most important role here. Let me draw a picture here, maybe it will make the things clear. Okay. So, okay, this is the bond I have made, okay, for let us say flow over a flat plate. Okay. So, what I am saying here is that we can divide into two parts. Okay, this is my inner layer, okay, and then you will have the outer layer. Okay. Here the viscosity is important, or viscous effects are important, okay, and they are not very important outside, okay, because the flow is turbulent here, right. So, this accounts for around 15% of your total region. Okay. So, it can be further divided into a layer very close to the wall, okay, which is called the viscous sublayer. Okay. Okay. And then we will have a buffer zone. Okay. This region is called the buffer zone. Okay. And then we will have something called the log layer. Okay. So, all these things come under there is something called law of the wall. Okay. And then you have the outer layer. So, there will be something called overlap layer. So, in between you will have there will be layer which is we call as the overlap layer, and then after that we will have something called law of the wake. Okay. Now, it so happens that in this region, okay, so in the inner layer, okay, if you go to very close to the wall, the viscosity dominates, that is in the viscous sublayer. Okay, viscous sublayer, the viscous stress dominates. In the outer layer, your turbulent stress dominates, as we have already discussed, and in the overlap layer, we have both stresses which are important, right. So, Prandtl and Karman did some study, and mostly on the understanding of the physical picture, and also about the dimension analysis, and they found out that in the inner layer, okay, for example, the flow is characterized by your wall shear stress. Let me write it W and rho and U and the distance from the wall. Okay. And in the outer layer, it is basically characterized by your pressure gradient. Okay, there is no, the pressure gradient does not play a role in the inner layer. Okay, the free stream pressure gradient. Okay, pressure gradient I will write as delta P. Okay, this is a free stream. Okay, and then we will have wall shear stress. Okay, and then bond layer thickness. These are the things that will dictate the outer layer. Okay. And based on that, what they did, they formulated the non-dimensional numbers, okay, and studied how the flow behaves. So, what I will do in the next class is I will formulate these boundary these non-dimensional numbers, equate it different terms, okay, and try to derive the laws that we have discussed, basically the law of the wall. Okay. I will not be discussing the law of the wake, because that is not terribly important in terms of modeling of this turbulence, but the law of the wall will be very important when we talk about the different turbulence models. Okay. So, let us meet in the next class. Thank you very much.